Picture floating through a universe where nothing has weight, where you, the air, the stars, even the phone in your hand could drift away like a feather in zero gravity. It sounds like science fiction, but this could have been our reality if not for one extraordinary cosmic rulebook written into the fabric of space itself. That rulebook is governed by something invisible, yet so powerful it shapes the very essence of what makes you me and everything in existence solid, something called the Higgs field. Here's the mind-bending part. This field isn't some distant force. It's everywhere right now, humming silently through the room you're in, through your body, through the screen you're watching. Without it, the universe as we know it wouldn't just feel different, it would cease to exist. Atoms would never clump together, stars wouldn't ignite. Life couldn't form, and yet, until just 50 years ago, we had no idea it was there. The story of how we uncovered this invisible architect of matter, how we went from total ignorance to rewriting the laws of physics, is one of humanity's greatest detective stories, filled with brilliant leaps of imagination, colossal machines, and a splash of cosmic luck. So how does it all work? Think of the Higgs field like an endless, invisible ocean filling every corner of the universe. Most particles, like electrons or quarks, swim through this ocean as if it's thick honey, slowing them down, giving them mass. Others, like photons, glide through effortlessly, remaining weightless. But here's where it gets wild. The Higgs field isn't just some passive backdrop. It interacts with particles, deciding which ones get to be heavy and which stay light. That means the reason you don't float off your chair right now isn't just gravity. It's because trillions of Higgs interactions are anchoring you to reality. And that's just the beginning. Over the next few minutes, we're diving deep into how this cosmic shadow shapes everything from the tiniest quark to the largest galaxy, and why uncovering its secrets didn't just change science but redefined what's possible. Strap in. This is the invisible force that built the universe as we know it, and you're about to see it in a whole new light. To understand why the Higgs field is such a game changer, we need to rewind to the building blocks of reality itself. Imagine the universe as a vast cosmic Lego set, where everything planets, light, is made of just a handful of fundamental particles. These are the tiniest, indivisible pieces of matter, like electrons swirling around atoms or quarks locked inside protons. For decades, physicists organized these particles into a framework called the Standard Model, a sort of periodic table for the subatomic world. But here's the catch. While the Standard Model brilliantly explained how particles interact through forces like electromagnetism or the strong nuclear force, it had a glaring hole. Nothing in the math explained why these particles had mass at all. Enter the Higgs field. Picture it like an invisible, universal molasses, a sticky, energetic medium that particles must push through as they move. Some particles, like the heavyweight quarks, slog through this molasses like a person wading through waist-deep syrup, gaining mass from the resistance. Others, like photons, the particles of light, are Olympic sprinters in comparison, darting through without a hint of drag, which is why light travels at, well, the speed of light. This elegant dance between particles and the Higgs field doesn't just give them mass, it fundamentally shapes how the universe behaves. Without it, particles would zip around weightlessly, never clumping into atoms, never forming stars, planets, or you. But the genius of the Higgs field isn't just in what it does, it's in how it rewrote the rules. For centuries, we thought of mass as an intrinsic property, like an object's color or shape. The Higgs mechanism flipped that idea on its head, revealing mass as something granted by an invisible interaction. It's the difference between assuming a car moves because it's just what cars do versus understanding it's the engine, the Higgs field, that makes motion possible. And just like an engine, the Higgs field isn't some abstract concept, it leaves fingerprints. In 2012, scientists at the Large Hadron Collider finally spotted its calling card, the Higgs Boson, a tiny ripple in the field that confirmed this cosmic molasses was real. That discovery didn't just fill a gap in a textbook, it unveiled the invisible hand sculpting the universe. Now, let's rewind to the 1960s, a time when physics was buzzing with excitement but also facing a glaring puzzle. Scientists had mapped out the forces governing the universe, from gravity to electromagnetism, yet one question lingered like an unsolved riddle: why does anything have mass at all? Enter Peter Higgs, a quiet, unassuming physicist at the University of Edinburgh, who stumbled upon an idea so radical it would rewrite our understanding of reality. Higgs wasn't alone in this quest. Around the same time, other brilliant minds, Francois Englert, Robert Brout, and later a team including Gerald Guralnick, Carl Hagen, and Tom Kibble, were all circling the same groundbreaking concept. Picture a group of detectives, each working independently but piecing together fragments of the same cosmic mystery. The key, a never-before-seen field lurking in the fabric of space. Higgs's eureka, a moment came while wandering the Scottish Highlands. He realized that if such a field existed, particles moving through it would slow down, gaining mass like swimmers fighting against a current. But here's where the story gets fascinating. Higgs's first paper on the idea was initially rejected by a major physics journal. The reviewers found it too speculative, too out there. Undeterred, he revised it, adding a crucial prediction. If this field existed, it should leave behind a telltale particle, what we now call the Higgs boson. That addition turned skepticism into intrigue, sparking a race to prove or disprove the theory. What's often forgotten is how collaborative science truly is. Higgs, Englert, Brout, and the others weren't rivals. They were part of an invisible chorus, harmonizing toward the same revolutionary tune. The real beauty of this discovery lies in its humility. The Higgs field doesn't demand attention. It's silent, omnipresent, working behind the scenes. Much like the scientists who uncovered it, the field's power is in its subtlety. Decades later, when the Large Hadron Collider finally confirmed the Higgs boson's existence, it wasn't just a victory for Higgs or his peers. It was a triumph for curiosity itself. Proof that even the universe's best-kept secrets can't hide forever from the stubborn, collective brilliance of human imagination. Here's an easy way to think about it. The Higgs field is like an invisible ocean, and the Higgs boson is like a splash in that ocean. The ocean itself, the field, is always there, stretching across the entire universe, subtly interacting with particles to give them mass. But if you disturb that ocean, like dropping a pebble into water, you create ripples. Those ripples are the Higgs boson, a tiny, fleeting burst of energy that proves the ocean exists in the first place. Imagine you're standing by a perfectly still pond. You can't see the water itself from a distance. It just looks like empty space. But the moment you toss a stone in, splashes erupt, sending waves outward. Those waves aren't the pond, they're evidence of it. That's exactly how the Higgs boson works. The field is the pond, always present but invisible. The boson is the ripple, a disturbance scientists can detect to confirm the field is real. Here's where things get even more fascinating. Unlike most particles we know, electrons, quarks, even photons, the Higgs boson doesn't stick around. It's more like a cosmic firework, appearing for just a fraction of a second before vanishing back into the field. That's why it took decades and a machine as massive as the Large Hadron Collider to spot it. Catching a Higgs boson is like trying to photograph a single raindrop in a thunderstorm. It's there, but blink and you'll miss it. Now, why does this distinction matter? Because the field and the boson play entirely different roles in shaping the universe. The Higgs field is the silent architect, working behind the scenes to give particles mass. Without it, everything would be weightless chaos. The Higgs boson, on the other hand, is like the field's signature, a way for scientists to confirm, yes, this invisible force is real. It's the difference between feeling the wind on your face and seeing a weather vane spin to prove the wind exists. And here's the kicker. The Higgs boson isn't just proof, it's a key to unlocking even deeper mysteries. By studying these fleeting ripples, physicists can figure out how strong the Higgs field is, how it behaves under extreme conditions, and even whether it might hold clues about the universe's earliest moments. So while the field does the heavy lifting, the boson is our flashlight, helping us see the invisible machinery that makes reality possible. Think of the Higgs field as an unseen cosmic crowd filling every inch of the universe, always present, always buzzing with energy. Now imagine different particles trying to move through this crowd. Some, like electrons, are like quiet, unnoticed guests slipping through with ease. They barely interact with the crowd, so they end up with very little mass, but others, like the top quark, the heaviest known fundamental particle, are like A-list celebrities entering a packed room. The moment they step in, the crowd surges toward them, grabbing their attention, slowing them down, making it hard for them to move. That resistance. That's mass. Here's how it works on a subatomic level. When particles like quarks or electrons travel through the Higgs field, they don't just glide past it, they actually exchange energy with it. Picture a game of catch where the Higgs field keeps tossing invisible mass tokens to the particle. The more tokens a particle catches, the heavier it becomes. Photons, the particles of light, refuse to play this game entirely. They don't interact with the field at all, which is why they remain weightless, zipping through the universe at light speed. This interaction isn't just a casual handshake, it's more like a dance where the Higgs field leads. The field isn't uniform, it's made up of countless tiny fluctuations like ripples in a pond. When a particle like a quark moves through it, those fluctuations temporarily cluster around it, creating a kind of drag. The stronger the interaction, the more the particle resists acceleration, which, according to Einstein's equivalence of mass and energy, means it gains more mass. What's truly wild is how precise this process is. The Higgs field doesn't just randomly assign mass, it follows strict rules embedded in the laws of physics. The W and Z bosons, which carry the weak nuclear force, get their substantial mass from interacting with the Higgs field in a specific, asymmetric way. Meanwhile, electrons, despite being fundamental particles, end up over 2,000 times lighter than a top quark because their interaction with the field is far weaker. And here's the kicker: without this finely tuned mechanism, the universe as we know it couldn't exist. Atoms rely on electrons orbiting nuclei at precise distances determined by their mass. If electrons were heavier, chemistry would change entirely. If protons and neutrons didn't have mass from their constituent quarks, atomic nuclei wouldn't form. Even the sun's nuclear fusion depends on particles having just the right mass to collide and fuse under extreme pressure. This isn't just theoretical, we've seen the Higgs field in action. When scientists at the Large Hadron Collider smashed protons together at nearly light speed, they weren't just creating explosions of energy. They were stirring up the Higgs field like pebbles tossed into a pond, producing Higgs bosons, those fleeting ripples that confirm the field's existence. Every time a Higgs boson appears, it's like the universe whispering, "See, this is how I give things weight." So next time you pick up an object and feel its heft in your hand, remember, you're not just sensing gravity. You're feeling the aftermath of trillions of particles interacting with an invisible field that permeates every corner of reality. A field that decides which particles get to be heavy, which stay light, and ultimately which rules the universe follows. Building something as big as a cathedral, as cold as outer space, and as precise as a Swiss watch, that's what it took to hunt down the Higgs boson. The Large Hadron Collider isn't just a machine. It's a 27-kilometer-long underground racetrack for protons, buried beneath the border of France and Switzerland. Picture this: trillions of protons, each smaller than an atom, are whipped into two beams racing in opposite directions at 99.9999% the speed of light. When those beams collide for a split second, they recreate conditions hotter than the center of the sun, conditions that haven't existed since the universe was a trillionth of a second old. Why go to such extremes? Because the Higgs boson isn't just hiding, it's elusive. Unlike electrons or photons, which stick around long enough to study, the Higgs boson vanishes almost instantly, decaying into other particles in less than a septillionth of a second. To catch it, scientists needed a machine that could generate millions of collisions per second, hoping that in that chaos, a handful of Higgs bosons might flicker into existence. That's like trying to find one specific grain of sand on a beach by briefly lighting it with a strobe. The engineering behind the LHC is as breathtaking as the science. Its superconducting magnets, chilled to -271 degrees Celsius colder than deep space, bend those proton beams with a force equivalent to 80,000 times Earth's magnetic field. The detectors, like ATLAS and CMS, are layered like onions, each designed to catch different debris from collisions. Some track charged particles, others measure energy. Together, they act like subatomic forensic labs, reconstructing what happened in those unimaginably brief moments after protons smashed together. But here's the real genius: the LHC doesn't just find particles. It tests the universe's rulebook. Every collision is an experiment, probing whether our theories, like the Standard Model, hold up or crack under pressure. When it confirmed the Higgs boson in 2012, it wasn't just checking a box. It proved that the Higgs Field, this invisible cosmic architect, wasn't just a clever idea, it was woven into reality itself. And the hunt isn't over. The LHC's collisions keep pushing boundaries, searching for cracks in known physics, hunting particles that might explain dark matter or hidden dimensions. It's a reminder that the universe's biggest secrets often hide in the smallest places, and sometimes you need a machine the size of a city to find them. The morning of July 4, 2012, crackled with a tension unlike any ordinary day at CERN. Hundreds of physicists crowded into the organization's main auditorium, while thousands more watched on live streams worldwide. The air hummed with whispers, decades of research, billions of dollars, and the collective hopes of the scientific community hung on what was about to be revealed. Then the moment arrived. Fabiola Gianotti, then head of the ATLAS experiment, and Joe Incandela of CMS took the stage. Their graphs and data plots told a story numbers alone couldn't. A tiny but unmistakable bump in the data, peaking at 125 gigaelectronvolts, the telltale signature of the Higgs boson. The room erupted, applause, tears, a standing ovation. This wasn't just a discovery, it was the culmination of a 50-year quest to answer one of physics' most fundamental questions. The Higgs boson's existence didn't just fill a gap in the Standard Model. It validated the entire framework, confirming that the universe really does use an invisible field to assign mass to particles. Journalists scrambled to explain the implications, headlines blared, and for a brief moment, particle physics dominated dinner table conversations worldwide. Even Peter Higgs, then 83 years old and famously reserved, wiped away tears as he admitted he never expected to see proof in his lifetime. But the real magic of that day wasn't just in the graphs. It was in how the discovery unfolded, a masterclass in scientific rigor. The teams didn't rush. They waited until the statistical significance hit 5 sigma, meaning there was only a 1 in 3.5 million chance the signal was a fluke. That's like flipping a coin and getting heads 22 times in a row. Every curve, every pixel of data was scrutinized, debated, and cross-checked by thousands of scientists across borders and languages, all converging on the same extraordinary conclusion. What's often overlooked is how this moment reshaped science itself. The Higgs boson wasn't just another particle, it was the first, and so far only, fundamental particle predicted entirely by theory before being found experimentally. Think about that. Mathematicians scribbled equations in the 1960s, and half a century later, a machine the size of a subway tunnel proved them right. It's like predicting the existence of a never-before-seen color, then inventing a microscope powerful enough to finally spot it. the aftermath rippled far beyond physics labs. The discovery silenced skeptics who dismissed the Higgs field as a ghost story and justified the staggering investment in pure science. It reminded the world that curiosity-driven research isn't just about answers, it's about asking better questions. Because now that we've found the Higgs, new mysteries emerge. Why is the boson so light? Does it interact with dark matter? Could there be other undiscovered fields? The universe, it turns out, is still full of secrets, but thanks to that summer day in 2012, we know we're asking the right questions. Let's take a step back and ask the most profound question of all. Why does any of this matter? The Higgs field isn't just some abstract idea tucked away in a physics textbook. It's the silent sculptor of the universe, the reason reality looks the way it does. Imagine a world without it. Particles would zip around at the speed of light, never slowing down, never sticking together. Atoms wouldn't exist because electrons, untethered by mass, would never orbit nuclei. Stars couldn't ignite because the delicate balance of nuclear fusion relies on particles having just the right amount of mass to collide and spark. Life as we know it wouldn't just be different, it would be impossible. Think of it like this: the Higgs field is the universe's rulebook for stability. Without it, every fundamental force we take for granted, gravity, electromagnetism, even the strong nuclear force that glues atoms together, wouldn't function the way they do. Protons and neutrons, the building blocks of matter, are made of quarks held together by particles called gluons. But here's the catch: those quarks get their mass from the Higgs field. No Higgs, no quark mass, no quark mass, no protons or neutrons, no protons or neutrons, no atoms, and no atoms. Well, you get the picture. This isn't just theoretical doom scrolling. We've seen glimpses of what a Higgs-less universe might look like in extreme environments like particle colliders. When scientists smash particles together at nearly light speed, they momentarily strip away the Higgs field's influence, recreating conditions similar to the universe's first chaotic moments after the Big Bang. In those fleeting instants, particles behave wildly, unshackled from the mass that normally anchors them. It's a window into how fragile our reality really is and how much we owe to this invisible field. But the Higgs field's importance goes even deeper. It's not just about whether particles have mass, it's about how much. The field isn't a one-size-fits-all force. It interacts differently with each particle, giving us the staggering variety we see in the universe. Electrons are light enough to zip around atoms, enabling chemistry. W and Z bosons are heavy enough to carry the weak nuclear force, driving radioactive decay and stellar fusion. If these masses were even slightly different, the cosmic recipe would fail. Stars might burn too fast or too slow. Molecules might never form. The universe would be a sea of featureless radiation, devoid of structure or life. Here's the kicker: the Higgs field might even hold clues to the universe's ultimate fate. Some theories suggest the field isn't static. It could exist in a false state, like a pencil balanced on its tip. If something tipped it into a lower energy state, it could trigger a catastrophic phase change, rewriting the laws of physics in an instant. Entire galaxies could vanish in a bubble of new reality expanding at light speed. Sounds like science fiction, maybe, but it's a reminder that the Higgs field isn't just part of the universe, it's a defining thread in the fabric of existence itself. So the next time you pick up a cup of coffee, remember, the weight in your hand, the heat on your fingers, even the light reflecting off the surface, all of it exists because an invisible field decided, billions of years ago, that particles should slow down just enough to build a universe worth living in. That's the quiet power of the Higgs field. It doesn't just give particles mass, it gives us a world. One of the biggest misconceptions about the Higgs field is that it's the universe's mass factory responsible for every bit of weight in existence. But that's not quite how it works. The Higgs field doesn't hand out mass like a cosmic vending machine. It's more like a selective bouncer at an exclusive club, deciding which particles get to be heavy and which stay lightweight. For example, most of the mass in your body doesn't actually come from the Higgs field at all. It comes from the energy binding quarks together inside protons and neutrons, a side effect of the strong nuclear force, not the Higgs mechanism. Here's where things get even more counterintuitive. Dark matter, that mysterious substance making up 85% of the universe's mass, doesn't seem to interact with the Higgs field at all. If it did, we'd have detected its signature by now. Similarly, the Higgs field has nothing to do with gravitational mass, the kind that makes apples fall or planets orbit. Gravity is a geometric effect caused by the curvature of spacetime, not a force mediated by Higgs interactions. So while the Higgs field is crucial for giving fundamental particles their mass, it's not the universal mass giver we sometimes imagine. Another myth that the Higgs field is some kind of cosmic molasses slowing everything down. In reality, particles aren't literally trudging through a sticky medium. The interaction is far more subtle, a quantum handshake where particles exchange virtual Higgs bosons, temporarily borrowing energy that manifests as mass. Think of it like a celebrity constantly being stopped for selfies. The delays add up, making them seem heavier in terms of momentum, but they're not stuck in physical syrup. And then there's the idea that the Higgs field explains why particles have mass. That's backward. The field doesn't explain the why, it reveals the how. The math tells us particles interact with the field, but we still don't know why electrons interact so weakly while top quarks interact so strongly. It's like knowing the rules of a game without understanding why those rules exist in the first place. The most persistent misconception might be this, that discovering the Higgs boson completed physics. Truth is, it opened more doors than it closed. The Higgs boson's mass, 125 times heavier than a proton, is oddly light compared to predictions. Some theorists think this hints at undiscovered particles or even parallel Higgs fields lurking in the quantum shadows. Others wonder if the Higgs could be a composite particle made of smaller, stranger things we've yet to find. So next time someone says the Higgs field gives everything mass, remember, reality is far messier and far more interesting than a simple soundbite. The Higgs isn't the end of the story, it's the key to a much bigger mystery we're only beginning to unravel. Rewind the universe to its very first moments, a seething, unfathomably hot soup of pure energy. In that primordial chaos, the Higgs field didn't exist yet. That's right, for a fleeting fraction of a second after the Big Bang, the universe was a place without mass, where particles raced at light speed, unburdened by weight. Then something extraordinary happened. As the cosmos cooled, an invisible phase transition rippled through space like water freezing into ice, and suddenly the Higgs field switched on. This wasn't just a minor tweak to reality, it was the moment the universe gained its rulebook. Think of it like a cosmic game of musical chairs. Before this transition, particles were like hyperactive kids buzzing around endlessly. But when the Higgs field emerged, it was as if chairs suddenly appeared. Some particles, like quarks and electrons, found seats interacting with the field and gaining mass. Others, like photons, kept zooming past, remaining weightless. This sorting didn't just assign properties, it dictated how the universe would evolve. Without this critical shift, the fundamental forces we know, gravity, electromagnetism, the strong and weak nuclear forces wouldn't have separated cleanly. The weak force, for instance, needed the Higgs field to give mass to W and Z bosons, allowing it to become distinct from electromagnetism. Here's where it gets wild. The Higgs field didn't just shape particles, it shaped time itself. In those first moments, the universe expanded exponentially during a period called inflation. Some theories suggest the Higgs field might have been the engine behind this expansion, its energy driving space to stretch faster than light. Then, as the field settled into its current state, that energy was released as heat, reheating the cosmos and setting the stage for matter to clump into atoms, stars, and galaxies. It's as if the Higgs field was both the architect and the construction crew, building the scaffolding for everything that followed. but the story doesn't end there. The Higgs field's emergence might hold clues to one of physics' biggest mysteries. Why is there more matter than antimatter? According to the Standard Model, the Big Bang should have created equal amounts of both, leaving the universe barren as they annihilated each other. Yet here we are. Some theories propose the Higgs field interacted differently with matter and antimatter, tipping the scales ever so slightly in favor of matter. If true, that means the Higgs field didn't just give us mass, it gave us existence, and there's an even stranger possibility. The Higgs field's current state might not be its final form. What if it's metastable, balanced precariously, like a marble resting on the edge of a bowl? Some calculations suggest that if the field were to shift into a lower energy state, it could trigger a catastrophic phase change, rewriting the laws of physics in an expanding bubble of new reality. This wouldn't just destroy stars and planets, it would unravel the very fabric of mass, space, and time. Don't panic, though. If it happens, it'll likely be trillions of years from now, long after the last stars burn out. So when you look up at the night sky, remember, those stars, those galaxies, even your own hands are here because of a quiet revolution that happened in the universe's first blink. The Higgs field didn't just assign mass, it set the stage for complexity, for structure, for life. And as we peer deeper into its origins, we're not just uncovering the past. We're glimpsing the fragile, beautiful conditions that made our reality possible. At the quantum level, the Higgs field isn't a calm, steady ocean, it's a boiling, frothing sea of chaos. Even in what we think of as empty space, the field is constantly writhing with quantum fluctuations, tiny disturbances where energy flickers in and out of existence. These aren't just random blips, they're the universe's way of balancing the books on an unimaginably small scale. And here's the twist. These fluctuations don't just happen around the Higgs field, they are the Higgs field, vibrating at its most fundamental level. Picture a trampoline stretched tight. Now imagine countless ants racing across it, each bounce sending ripples through the fabric. That's the Higgs field in action. But in this analogy, the ants are virtual particles, short-lived bursts of energy that borrow from the universe's quantum ledger, popping into existence just long enough to interact with the field before vanishing again. These aren't real particles in the traditional sense. They're more like cosmic IOUs, here one femtosecond, gone the next, yet their fleeting presence has real consequences. Every time a virtual particle interacts with the Higgs field, it momentarily distorts the field's value in that tiny patch of space, changing how other particles experience mass in that instant. This isn't just theoretical hand-waving. We've actually measured these effects. Take the electron's mass. It's not a fixed number stamped on a cosmic ID card. It's more like an average over trillions of these quantum interactions. Sometimes, thanks to fluctuations, an electron might momentarily weigh a fraction more or less as virtual particles tweak the Higgs field around it. It's as if the universe is constantly recalculating the rules on the fly, with mass itself being a dynamic, negotiable property rather than a rigid constant. The wildest part, these fluctuations might hold the key to one of physics' biggest unsolved problems, the hierarchy problem. The Higgs boson is shockingly lightweight compared to what quantum math predicts, about 10 quadrillion times lighter than it should be. One leading theory suggests a cosmic cancellation is at work, where opposing fluctuations in the Higgs field perfectly balance out, leaving behind just the faint whisper of mass we observe. It's like two singers hitting discordant notes that somehow cancel each other to leave perfect silence. If true, it implies an invisible symmetry woven into the fabric of reality, one we're only beginning to decode. But here's where it gets even stranger. These quantum fluctuations aren't confined to the microscopic realm. On the smallest scales, space itself might be a foam of bubbling Higgs field distortions, with entire particles appearing and disappearing in a frenzied dance. Some theories even suggest that in these fleeting moments, the laws of physics as we know them might briefly break down, offering glimpses of deeper, hidden layers of reality. It's a reminder that the Higgs field isn't just a backdrop. It's an active participant in shaping the universe moment by quantum moment. And every time you move your hand, you're not just pushing against air, you're navigating a sea of invisible turbulence where mass itself is a fleeting agreement between particles and the chaos beneath. Of all the forces in the universe, gravity is the cosmic underdog, astonishingly feeble compared to its siblings. A simple fridge magnet can defy the gravitational pull of our entire planet, lifting a paperclip effortlessly. Yet gravity shapes galaxies, bends light, and governs the cosmos on the largest scales. So why is it so weak? This enigma, known as the hierarchy problem, isn't just a curiosity, it's a glaring crack in our understanding of physics, and the Higgs field sits right at the heart of it. Picture the fundamental forces as siblings. Electromagnetism and the nuclear forces are the boisterous, short-range powerhouses governing atoms and chemical bonds. Gravity, meanwhile, is the quiet, long-distance sibling present everywhere, yet billions of times weaker than the others. The math suggests a reason. Gravity's apparent weakness might stem from its origin in the fabric of spacetime itself, while other forces arise from particle interactions. But here's where the Higgs field throws a wrench into the story. The Higgs field's energy density, the sheer amount of energy stored in its omnipresent hum, should theoretically make gravity far stronger than we observe. Quantum calculations predict the Higgs field's energy should warp spacetime so intensely that the universe would collapse into a black hole, yet it doesn't. This means either our math is missing something fundamental, or there's a cosmic balancing act we haven't discovered. One leading theory suggests the existence of hidden dimensions, tiny, curled-up realms of space beyond our perception. In this scenario, gravity's strength might be diluted because it leaks into these extra dimensions, while other forces, confined to our familiar three-dimensional world, remain robust. The Higgs field could be the bridge between these layers, its energy density stabilized by interactions we can't yet see. It's like gravity is a sound wave echoing through a vast cathedral, while other forces are vibrations trapped in a single room. But there's another twist. The Higgs boson's mass, a mere 125 gigaelectronvolts, is suspiciously light compared to predictions. Without some invisible mechanism fine-tuning the numbers, quantum fluctuations should have sent the Higgs boson's mass skyrocketing to scales a quadrillion times larger. This suggests either an exquisite, unexplained cancellation of effects or the presence of undiscovered particles like supersymmetric partners acting as counterweights in the cosmic equation. The hierarchy problem isn't just academic. Solving it could unveil truths about the universe's stability or its eventual fate. If the Higgs field's energy density is precariously balanced, even a slight shift could trigger a catastrophic phase transition, rewriting physics in an instant. Or perhaps the answer lies in a grand unified theory, where all forces merge at energies so high they've left only faint traces in our low-energy world. For now, the hierarchy problem remains one of physics' most tantalizing loose ends, a reminder that the universe's deepest secrets often hide in plain sight, woven into the very forces we thought we understood. And as we probe further, the Higgs field may yet reveal whether gravity's weakness is a quirk of nature or a clue to something far stranger. The standard model is like a nearly perfect map of the subatomic world, except for the blank spaces where dragons might be. We've charted the Higgs field, measured its quirks, and yet deep mysteries remain. Why is gravity so weak compared to other forces? Why does the Higgs boson weigh what it does? The answers might lie beyond the edges of our current physics, in theories so bold they rewrite reality itself. Take supersymmetry, one of the most tantalizing ideas on the table. It proposes that every known particle, electrons, quarks, even the Higgs boson, has a hidden twin, a superpartner with slightly different properties. These shadow particles could solve multiple puzzles at once, For instance, the lightest superpartner might be the elusive dark matter that binds galaxies together. Others could act like invisible counterweights, stabilizing the Higgs field's energy and explaining why it doesn't warp the universe into oblivion. Imagine a cosmic scale where every visible particle has an unseen counterpart, perfectly balancing the equation. The math is elegant, but here's the catch. After decades of searching, colliders haven't found a single superpartner. That doesn't mean they're not there, just that they might be heavier or stranger than we anticipated. Then there's the wild card, extra dimensions. We're used to thinking in 3 dimensions of space and 1 of time, but what if there are more? Tiny, curled-up realms too small to see, like the folds in a crumpled sheet of paper. In some theories, gravity's puzzling weakness could be because it's leaking into these hidden dimensions, diluted across realities we can't perceive. The Higgs field might be the gatekeeper, its behavior shaped by interactions not just in our world, but in these unseen layers. Picture a tuning fork vibrating in a room. You hear the note, but if the sound escapes through a hidden door, the music changes. Similarly, the Higgs field's properties could be echoes of a deeper, multidimensional symphony, but the rabbit hole goes deeper. Some theorists suggest the Higgs boson isn't fundamental at all. It might be a composite made of even smaller particles bound together by a new, undiscovered force. This idea, called Technicolor, imagines a hidden atomic forge where Higgs-like particles are hammered into existence, just as protons are built from quarks. If true, it would mean our current Higgs is just the tip of an iceberg with a whole shadow physics lurking beneath. And let's not forget the cosmic lottery, the multiverse. If our universe is one bubble in an endless froth of realities, each with different laws, the Higgs field's value might simply be luck, a random draw that gave us a stable, life-friendly cosmos. Other bubbles might have Higgs fields too strong, crushing particles into black holes, or too weak, leaving matter weightless and unformed. We're here because our numbers came up, no deeper reason required. It's a controversial idea, but it underscores how strangely fine-tuned our Higgs field seems, as if the universe conspired to make chemistry and life possible. What's thrilling is that these aren't just thought experiments. The Large Hadron Collider and future machines like the proposed Future Circular Collider are hunting for clues, tiny deviations in Higgs behavior, unexpected particle decays, or energy spikes that could signal these beyond the standard model worlds. Every anomaly in the data is a potential trailhead leading to physics we've barely imagined. The Higgs field, once a missing puzzle piece, has become a flashlight illuminating just how much we don't know. And that's the beauty of science. The deeper we dig, the bigger the mystery gets. Most people first heard about the Higgs field through its flashy nickname, the God particle, a phrase that's equal parts poetic and misleading. Coined by physicist Leon Lederman in the 90s, the term was meant to capture the field's elusive, almost mythical role in shaping reality. But the name stuck for another reason. It made headlines. Publishers loved the drama, while scientists cringed at the implication that the Higgs held some divine significance. In truth, the Higgs field isn't a cosmic creator. It's more like the universe's invisible rulebook, quietly enforcing how particles behave. Yet that tension between scientific nuance and pop culture spectacle has shaped how the world sees this fundamental force. Take the Big Bang Theory, where Sheldon Cooper scribbles Higgs equations on a whiteboard between punchlines. The show gets credit for name-dropping real physics, but it often reduces the Higgs to a nerdy punchline, something to impress Penny with, not explain. Most episodes gloss over the field's mind-bending implications, opting for quick quips about bosons instead of delving into why this discovery rewrote textbooks. It's a classic case of pop culture skimming the surface, turning a revolution in understanding into a background prop for geek humor. Then there's Angels and Demons, Dan Brown's thriller where antimatter harvested from CERN becomes a weapon. While the Higgs field isn't the villain, the book and film turbocharge the myth that particle physics is a high-stakes game of cosmic danger. Real-world Higgs research couldn't create apocalyptic explosions, but the dramatic flare stuck. Even documentaries sometimes lean into the hype, framing the Higgs boson as a key to the universe's secrets, without explaining that it's one piece of a much larger puzzle. But pop culture's obsession with the Higgs isn't all oversimplification. It's also a testament to how deeply this idea resonates. When Futurama jokes about the Higgs Boson Tavern, or The Simpsons shows Homer accidentally destroying the Higgs Boson, a beer particle, they're nodding to something remarkable, a concept so foundational it's become shorthand for cutting-edge science itself. These portrayals, even when silly, reflect a cultural fascination with the invisible forces that literally hold our world together. The irony: the more the Higgs field appears in movies and memes, the more its real significance fades behind the theatrics. You won't find blockbusters exploring how the Higgs field's quantum fluctuations might hint at extra dimensions, or how its energy could one day rewrite the laws of physics. Those stories are arguably more dramatic than the fiction, they're just harder to package in a 2-hour script. So while pop culture has brought the Higgs into the mainstream, it's also left us with a lingering question. How do you celebrate a scientific breakthrough without losing its depth? Maybe the answer lies not in dumbing it down, but in trusting audiences to embrace the wonder of the real story, one where the truth is stranger and far more thrilling than any nickname could capture. Right now, deep beneath the French-Swiss border, engineers are working on the biggest upgrade to the Large Hadron Collider since it first powered on. The high-luminosity LHC isn't just a tune-up, it's a complete reinvention designed to smash protons together at 10 times the current rate. That means trillions more collisions, and with them, a flood of Higgs bosons waiting to be studied with precision we've never dreamed of. This isn't about finding the Higgs again, it's about interrogating it, uncovering every last secret this particle has kept hidden. Think of it like upgrading from a flip phone to the latest smartphone overnight. The original LHC gave us blurry snapshots of the Higgs, enough to confirm its existence but leaving countless questions unanswered. The high-luminosity version will be like putting the Higgs under an electron microscope, revealing details down to a level that could rewrite physics textbooks. Scientists will measure how the Higgs interacts with lighter particles like muons with razor-sharp accuracy. They'll hunt for ultra-rare decays moments when the Higgs transforms into particles we've barely glimpsed. And if there's even a hint that the Higgs isn't behaving exactly as predicted, that could be the crack in the standard model that leads us to entirely new physics: dark matter, hidden dimensions, or forces we've never imagined. But the LHC's upgrade is just the beginning. Across the globe, next-generation colliders are already on the drawing boards. China's proposed circular electron-positron collider would be a Higgs factory, churning out millions of them in pristine conditions, free from the messy debris of proton collisions. Japan's International Linear Collider, if built, would fire electrons and positrons straight into each other, creating cleaner collisions to measure the Higgs properties down to the decimal point. And Europe's Future Circular Collider, a 91-kilometer monster 4 times the size of the LHC, could push energies so high they'd recreate conditions last seen a trillionth of a second after the Big Bang. What's thrilling is that these machines aren't just about brute force, they're about finesse. The high-luminosity LHC, for example, uses cutting-edge superconducting magnets to squeeze proton beams into thinner, denser strands, increasing collision chances without needing more energy. Its upgraded detectors, like Atlas and CMS, will be outfitted with silicon sensors so precise they could track a particle's path through a single pixel. It's like trying to photograph a hummingbird's wings with a camera that captures every feather at 10,000 frames per second, and the stakes nothing less than the universe's deepest mysteries. If the Higgs couples to dark matter, these experiments could catch it in the act. If extra dimensions exist, subtle anomalies in Higgs behavior might betray their presence. Some theories even suggest multiple Higgs bosons could be hiding in plain sight, each with slightly different masses, like shadows of the one we've found. Every decimal point of precision is another chance to stumble upon something revolutionary. So while the discovery of the Higgs boson felt like an ending, it was really an invitation, a doorway cracked open to a much stranger, richer reality waiting beyond. The next decade of collisions won't just refine what we know, they might reveal everything we've missed. Among the universe's greatest unsolved puzzles, dark matter looms largest, an invisible substance outweighing ordinary matter 5-1, its gravity holding galaxies together. Yet despite decades of searching, we've never directly detected it. Here's where the Higgs field enters the story. What if this invisible architect of mass also holds the key to dark matter's identity? One compelling idea gaining traction is the Higgs portal model. Picture the Higgs field as a cosmic receptionist, deciding which particles get to interact with our visible world. According to this theory, dark matter particles could be like invisible guests at a party, normally ignoring everyone except when the Higgs introduces them to ordinary matter. In technical terms, dark matter might not feel electromagnetism or the strong nuclear force, but it could occasionally exchange Higgs bosons with regular particles, leaving faint fingerprints we're only now learning to trace. How would this work in practice? Imagine dark matter particles drifting through Earth like ghosts. Most pass straight through unnoticed, but a rare few might bump into atomic nuclei via Higgs-mediated interactions. These collisions would be vanishingly subtle. Think a snowflake tapping a window, but ultra-sensitive detectors buried deep underground, shielded from cosmic noise, are actively hunting for such whispers. Experiments like ELUX Zeppelin and Xeno-NNT use vats of liquid xenon as dark matter microphones, waiting for the telltale flash of light when a nucleus recoils from an unseen impact. The beauty of Higgs portal models is their elegance. They don't invent elaborate new physics. They repurpose the Higgs field as a universal translator between known and unknown realms. Some versions propose dark matter as a sibling to the Higgs boson, a heavier, stable particle forged in the same primordial symmetry breaking that gave the Higgs its properties. Others suggest dark matter could be a shadowy twin of neutrinos, acquiring mass through Higgs interactions while remaining otherwise aloof, but the plot thickens. If dark matter talks to the Higgs field, it might leave clues in space itself. When two dark matter particles collide in distant galaxies, they could annihilate into Higgs bosons, which then decay into gamma rays. Telescopes like Fermi LT are scanning the cosmos for unexplained gamma ray excesses, mysterious glows that could be Higgs-fueled dark matter fireworks. Similarly, the Higgs field's quantum fluctuations might subtly alter how dark matter clumps around galaxies, creating density patterns visible in gravitational lensing surveys. Not all theorists are convinced. Critics point out that if dark matter interacts via the Higgs, it should have shown up in particle colliders by now, unless it's extraordinarily light or the coupling is fantastically weak. Alternative models propose dark matter might ignore the Higgs entirely, communicating through entirely new forces or even extra dimensions. Yet the Higgs portal remains a compelling roadmap because it leverages known physics rather than conjuring untested phenomena. What makes this connection thrilling is its testability. Upgraded colliders could produce Higgs bosons with just enough energy to spit out dark matter particles, glimpsed only as missing energy in detectors. Precision measurements of the Higgs decay rates might reveal hidden channels where it morphs into invisible stuff. And if dark matter's mass comes from the Higgs field, that implies a specific range for its heft, narrowing the search from a cosmic haystack to a manageable handful of straw. We're left with a tantalizing possibility. The same field that explains why you have weight might also explain why 85% of the universe's matter is unseen. Unraveling this link wouldn't just solve two mysteries at once. It would reveal a hidden layer of cosmic dialogue, where the ordinary and the shadow universe exchange whispers through the Higgs. And every experiment brings us closer to eavesdropping. You might think smashing protons in a giant underground ring sounds like pure science with no practical payoff, but the hunt for the Higgs has spun off technologies that now touch millions of lives. Take medical imaging. The superconducting magnets developed for particle accelerators became the backbone of modern MRI machines. Those powerful magnets, chilled to temperatures colder than outer space, originally kept proton beams on track in colliders. Today, they generate the precise magnetic fields that let doctors peer inside the human body without a single cut, revolutionizing how we diagnose everything from torn ligaments to brain tumors. Then there's particle detectors themselves. The same silicon sensors built to track subatomic debris at CERN now help spot cancers earlier than ever. These ultra-sensitive chips, designed to catch fleeting particles, were adapted into PET scanners that trace radioactive traces in the body, revealing tumors at microscopic scales. It's a hauntingly beautiful twist. Technology created to study the universe's birth now helps save lives by spotting rogue cells before they spread. But the most unexpected spin-off. The World Wide Web. Tim Berners-Lee invented it at CERN specifically to help physicists share Higgs collision data across continents. The problem: scientists in different countries needed instant access to the same experiments. Berners-Lee's solution, hypertext links and HTML, didn't just connect labs, it rewired human civilization. Every tweet, every streaming show, every online bank transaction traces back to a tool built for Higgs hunters. Even cancer treatments owe a debt to Higgs research. Proton therapy, which zaps tumors with pinpoint accuracy, uses accelerator tech to steer charged particles. Unlike traditional radiation, which damages healthy tissue, these proton beams, tuned by hardware derived from colliders, dump their energy precisely where doctors aim, sparing surrounding organs. It's as if the precision needed to collide protons at light speed found a second life healing human bodies, and the breakthroughs aren't slowing down. The cryogenics that keep the LHC's magnets superconducting are now cooling quantum computers. Advanced machine learning algorithms, first trained to sift Higgs signals from noise, today power everything from fraud detection to drug discovery. Even radiation-resistant materials developed for detectors shield astronauts on the International Space Station. The lesson here is profound. When we chase fundamental questions about the universe, the tools we build often outshine the answers we seek. The Higgs field might explain why we have mass, but the technologies born from its pursuit are busy reshaping medicine, computing, and global communication. That's the hidden power of pure science. It doesn't just reveal nature's secrets. It hands us the keys to reinvent our world. $13 billion is a staggering price tag, enough to build several hospitals, fund renewable energy projects, or even send multiple missions to Mars. So when critics ask whether the Large Hadron Collider was worth it just to find one particle, it's a fair question. The Higgs discovery didn't cure diseases or put food on tables, and in a world grappling with climate change, poverty, and pandemics, pouring billions into abstract physics can seem indulgent. Even some scientists argue the money could have been better spent on applied research with immediate societal impact. But here's the counterpoint. History shows that chasing fundamental questions often yields unexpected, transformative rewards. When Michael Faraday toyed with electromagnetism in the 1800s, skeptics saw no practical use until his useless experiments led to electric grids powering the modern world. The same goes for quantum mechanics, which seemed purely theoretical until it gave us transistors, lasers, and every digital device we rely on today. The Higgs field might feel detached from daily life now, but its implications could ripple through future technologies we can't yet imagine. Then there's the human factor. The LHC didn't just produce data, it inspired a generation. Thousands of students worldwide dove into physics because of the Higgs Boson's discovery, and collaborations across borders showed science's power to unite. The project pushed engineering limits too, from cryogenics to computing, leaving behind breakthroughs now used in medicine, AI, and materials science. That $13 billion wasn't just spent on a particle hunt. It built infrastructure for innovation that will outlive the collider itself. Still, the debate isn't black and white. Some physicists quietly worry the Higgs overshadowed cheaper, high-reward experiments like neutrino studies or quantum computing that got less funding amid the LHC's dominance. Others note that while the discovery filled a key gap in the standard model, it didn't immediately unlock new physics like supersymmetry or extra dimensions, leaving some disillusioned. Yet perhaps the most compelling defense comes from the cosmos itself. Understanding the Higgs field isn't just academic, it's a window into the universe's stability. If the field's energy is metastable, as some data suggests, it could mean our reality is a fragile bubble in a multiverse. That's not just philosophy, it's a potential roadmap for humanity's survival, hinting at cosmic risks we might one day need to navigate. So was it worth it for pure knowledge alone? The chance to decode why atoms, stars, and we exist? Many would say yes, but the real answer lies in the long game, where today's useless mysteries become tomorrow's revolutions. The Higgs field shaped the universe once. Its discovery might shape our future in ways we're only beginning to glimpse. Right now, the Higgs field hums along at a seemingly stable energy level, like a ball resting comfortably at the bottom of a valley. But what if that valley isn't the lowest point possible? Some calculations suggest the field might be trapped in a false vacuum, a precarious state where it's temporarily stable but not truly at its lowest energy. Think of it like a marble balanced on the edge of a bowl. It's not moving right now, but the slightest nudge could send it rolling into a deeper, more stable position. And here's the unsettling part. If that shift ever happened, it wouldn't just tweak physics, it could rewrite reality itself. This scenario, called vacuum decay, begins with a tiny quantum fluctuation, a random blip where the Higgs field drops into its true lowest energy state. Like a spark in dry grass, that blip would create a bubble of new physics, expanding outward at light speed. Inside that bubble, the laws of nature would be unrecognizable. Particles might lose mass entirely, atoms could disintegrate, and the fundamental forces holding matter together might unravel. The bubble's edge wouldn't just destroy everything it touched, it would erase the very rules that make destruction meaningful. One moment you're sipping coffee, the next the concept of coffee no longer exists in any form we'd understand. Now, before you panic, consider the timescales involved. If vacuum decay happens, it's likely trillions of years away, long after stars burn out and galaxies fade to darkness. The universe today is still young and energetic, with the Higgs field showing no signs of instability. Plus, that hypothetical true vacuum state might not even exist. Some theories suggest our current Higgs energy is the lowest possible, making vacuum decay a cosmic non-issue. But the real intrigue lies in what this tells us about the universe's fragility. The Higgs field's potential instability hints that our reality might be one possible configuration among many, a single page in a vast book of physics. Other pages could host entirely different laws with different forces, particles, or dimensions. Some cosmologists even speculate that vacuum decay could be how new universes are born, with each bubble of true vacuum birthing its own cosmos. Experiments at the Large Hadron Collider are quietly probing this existential puzzle. By measuring the Higgs Boson's mass with extreme precision, down to the tiniest decimal, scientists can calculate whether the field is stable, metastable, or teetering on the brink. Currently, data suggests we're in a metastable state, safe for now, but not necessarily forever. That uncertainty isn't just a theoretical curiosity. It's a reminder that the universe's deepest workings are still a work in progress, and the Higgs field, silent and invisible, holds the pen. The discovery of the Higgs boson didn't just revolutionize physics, it became a gateway to inspire the next generation. CERN educational outreach transforms abstract concepts into hands-on adventures, proving you don't need a PhD to explore the frontiers of science. Take their virtual LHC tours, where students worldwide strap on VR headsets and step inside the collider's cavernous tunnels. Suddenly, those 27 kilometers of superconducting magnets and detectors aren't just specs on a page. They're a playground of science, with viewers maneuvering around proton beams like subatomic traffic controllers. Teachers report students who'd never shown interest in physics suddenly debating how calorimeters catch particle showers, all because they got to stand where discoveries happen. But the magic doesn't stop there. Citizen science initiatives like Higgs Hunters invite anyone with an internet connection to sift through real LHC data. Volunteers scour particle collision images for oddities, patterns, algorithms, might miss potentially spotting anomalies that lead to new discoveries. It's crowdsourcing meets cosmic exploration, with over 100,000 participants contributing to published research. One high schooler in Norway flagged an unusual event later confirmed as a rare Higgs decay, proving inspiration isn't a one-way street from scientists to the public. Sometimes it flows back. Universities have amplified this momentum with Higgs-themed programs tailored to different ages. The University of Liverpool's Physicists in Primary initiative uses playful analogies, like comparing the Higgs field to a classroom of students handing rumors to explain mass-giving interactions. Meanwhile, MIT's Particle Fever workshops turn cafeterias into makeshift cloud chambers, letting kids track cosmic rays with dry ice and rubbing alcohol. These aren't dumbed-down lectures, they're immersive experiences showing science as a living, evolving process. The ripple effects are measurable. Applications for physics degrees surged after the 2012 Higgs announcement, with many citing CERN open data policies as their spark. Teachers now use Higgs-related lesson plans to demystify quantum concepts, framing quarks and bosons not as intimidating jargon but as characters in nature's grand story. Even art schools collaborate with projects like Colliding Particles, blending documentary filmmaking with accelerator physics to humanize the research process. What makes this outreach revolutionary isn't just the science, it's the philosophy behind it. By treating the Higgs as a shared human achievement rather than an ivory tower secret, these programs redefine who gets to participate in discovery. When a 7th grader in Mumbai troubleshoots a detector simulation or a retiree in Buenos Aires tags potential Higgs events, they're not just learning, they're helping write the next chapter of physics. And that's the ultimate lesson. The universe's mysteries belong to everyone willing to explore them. The very notion of empty space collapses under the weight of the Higgs field. What we once imagined as a sterile void, the blank canvas between stars, is now revealed as a seething, vibrant medium, more like an invisible ocean teeming with unseen activity. This realization shatters classical physics' tidy separation of something and nothing. The Higgs field transforms the vacuum of space from a passive backdrop into an active participant, whispering to particles, nudging them into having mass, and ultimately determining the architecture of reality itself. Consider how this shifts our philosophical grounding. For centuries, thinkers from Aristotle to Newton framed empty space as mere absence, a stage where matter performed. But the Higgs field demands we reconsider. What if the stage is the performance? Its omnipresence means there's no true emptiness, only layers of interaction too subtle for our senses. Even in the deepest voids between galaxies, the Higgs field thrums with potential, a ghostly presence turning the universe into something more akin to a quantum symphony, where silence is never truly silent. This blurs boundaries in startling ways. If the Higgs field gives particles their mass by interacting with them, then an electron's solidity isn't an intrinsic property. It's a relationship, a dance between the particle and the field. In this light, matter isn't just in space, it's of space, an emergent feature of deeper, invisible dynamics. The chair you're sitting on feels solid, not because it's fundamentally stuff, but because countless particles are entangled with an all-pervading field that confers heft to their existence. The implications ripple into metaphysics. The Higgs field suggests reality is less a collection of discrete objects and more a network of interactions. Buddhist philosophers and quantum physicists suddenly find common ground. The idea that things have no independent, fixed nature, only relational properties shaped by context. Even the vacuum isn't truly empty, it's a simmering reservoir of virtual particles and quantum fluctuations, with the Higgs field underpinning it all. But here's the real mind-bender. If the Higgs field is everywhere, then what we call space isn't passive nothingness, it's an active medium with measurable energy. Einstein showed us that space can curve and ripple. Now, quantum field theory tells us it's also alive with hidden activity. The Higgs field doesn't just fill space, it defines it, shaping how particles move, interact, and persist. This forces us to ask, is the universe a place where things happen, or is it the happening itself? Perhaps most humbling is how the Higgs field exposes our perceptual limits. Human intuition is wired for a middle-sized world, where tables are solid and emptiness is, well, empty. But the closer we look, the more the universe resists these categories. The Higgs field is a reminder that reality operates on rules far stranger than our senses can grasp, and that every time we peel back a layer, we find not simplicity but deeper, richer complexity. In the end, the Higgs field doesn't just give particles mass, it gives us a new lens to see the universe, not as a static stage, but as a dynamic, participatory phenomenon where nothing is the most interesting thing of all. In October 2013, a quiet 84-year-old physicist named Peter Higgs received a phone call that would immortalize him in science history. The Nobel Prize Committee was on the line, informing him he'd won physics' highest honor for predicting the existence of the particle and field that now bore his name. Characteristically, Higgs was nowhere to be found for the announcement. He'd slipped out to avoid media frenzy, later admitting he forgot the Nobel calls were scheduled that day. When reporters finally tracked him down, his response was pure Higgs, unassuming, almost embarrassed by the spotlight. "It's very nice to be right sometimes," he shrugged, as if his half-century-old theory hadn't just reshaped humanity's understanding of reality. The Nobel wasn't just a personal triumph, it was a victory lap for collective brilliance. The committee carefully split the prize between Higgs and Francois Inglet, honoring their parallel theoretical breakthroughs in 1964. But they could have easily included half a dozen others. Robert Brout, who collaborated with Inglet, had passed away by 2013. Nobel rules forbid posthumous awards. Gerald Guralnick, Carl Hagen, and Tom Kibble published nearly identical work just months later. The deliberate choice to recognize multiple theorists subtly underscored science's collaborative nature. No discovery springs fully formed from one mind. What made Higgs's Nobel unusual wasn't just the weight, it was how the prize celebrated patience itself. Most Nobels land within years of a breakthrough. Higgs waited 49, living long enough to see his idea evolve from wild speculation to accepted fact. The delay wasn't oversight, it reflected the Nobel Committee's ironclad rule: no prize without proof. Until the Large Hadron Collider spotted the boson in 2012, the Higgs field remained elegant math, not confirmed physics. That caution sent a powerful message: science rewards not just creativity but rigor. The ceremony itself was a study in contrasts. Inglet, ever the showman, charmed the Swedish royal family with witty remarks. Higgs, allergic to pomp, looked like he'd rather be back in Edinburgh grading papers. Yet their joint press conference revealed profound mutual respect. When asked about competition, Inglet brushed it aside. "We were all drinking from the same well." Higgs nodded, adding that the boson's discovery belonged equally to the thousands of engineers and experimentalists who built the LHC. It was a poignant reminder that theories guide but proof builds. Behind the glittering medals lay a deeper story about how science really progresses. The Nobel shone a light on theorists, but CERN army of technicians, the welders who sealed superconducting pipes, the programmers who filtered collision data, received no Stockholm invitations. Higgs knew this better than anyone. During his acceptance speech, he devoted more time praising the invisible contributors than his own work. That humility, more than any prize, captured the spirit of the hunt, a half-century relay where each generation passed the baton, not knowing if the finish line would ever come. Perhaps the most telling moment came after the fanfare faded. Journalists asked Higgs what he'd do with the prize money. Expecting grand plans, they got classic Higgs, pay bills probably. Then, almost as an afterthought, he mused that maybe he'd buy a nice bottle of wine. It was a fitting coda. For a man who'd unlocked the universe's secrets, life's simple pleasures still mattered most, a quiet testament to the human behind the legend. Let's make the invisible visible for a moment. Imagine your screen is a window into a cosmic lab where we can simulate how particles gain mass from the Higgs field. Picture a grid of glowing lines stretching infinitely in all directions. That's our stand-in for the Higgs field, the universe's hidden substrate. Now, watch as a tiny dot representing an electron glides across this grid. At first, it zips effortlessly, barely disturbed, but the moment it interacts with the grid's lines, something changes. The dot starts to slow, as if dragging an invisible weight. That's mass emerging in real time, the electron's lightness coming from its weak handshake with the field. Now, reset the simulation. This time, a heavier dot appears, a top quark, the heaviest known particle. As it moves through the grid, the lines seem to cling to it like vines tangling around a hiker's boots. The quark's path becomes sluggish, laborious. That's the Higgs field in action. The stronger the interaction, the more mass the particle gains. The quark isn't just moving, it's fighting against the universe's invisible molasses with every step. Now let's flip the script. Send a photon, a particle of light, through the same grid. No matter how you tweak the simulation, the photon never slows. It streaks across the screen unfazed. Why? Because photons refuse to interact with the Higgs field entirely. They're the ultimate cosmic rebels, zipping through the universe's sticky web without picking up an ounce of mass. Here's where it gets interactive. Imagine you could adjust the Higgs field's stickiness with a slider. Crank it up, and suddenly even electrons crawl like they're wading through tar. Turn it down and quarks start sprinting like photons. What happens if you shut it off completely? Chaos. Particles lose all mass, zooming at light speed. Atoms unravel, stars blink out. The universe as we know it dissolves into a featureless haze of weightless energy. This isn't just a thought experiment, it's a glimpse into how finely tuned our reality is. The Higgs field's strength isn't arbitrary. It's set to a value that allows atoms, chemistry, and life to exist. Tweak it even slightly and everything changes. That's the power of this invisible framework. It's not just part of the universe's rules. It's the architect that decided the rules could exist at all. Now picture one final twist. What if there are regions of space where the Higgs field's strength isn't uniform? Some theories suggest cosmic defects like wrinkles in the field's fabric, where particles might behave bizarrely, gaining or losing mass unpredictably. While we've never observed this, it's a haunting reminder that the Higgs field isn't just a passive stage. It's a dynamic, living structure, one we're only beginning to map. So the next time you feel the weight of your phone in your hand, remember, you're not just holding a device, you're holding a network of trillions of particles, each tethered to reality by an invisible quantum conversation with the Higgs field. And thanks to simulations like this, we can finally see the unseeable, the silent force that makes the universe solid, stable, and strangely, beautifully just right. What if the Higgs field isn't just a cosmic rulebook? What if it's a dial we could turn? Imagine tweaking its strength like adjusting the gravity in a sci-fi movie. Suddenly, particles lose mass, becoming nearly weightless. Could we engineer a bubble where the Higgs field weakens just enough to let a spacecraft slip through space-time with less resistance? It sounds like warp drive fantasy, but here's the wild part. The math isn't entirely fiction. Some theories suggest exotic matter with negative energy, something we've glimpsed in quantum experiments, might locally distort the Higgs field, thinning that invisible molasses around an object. The catch: we'd need energy levels dwarfing anything our colliders can produce, and we'd risk unraveling the very atoms holding the ship together. One miscalculation, and your spacecraft might dissolve into a cloud of weightless particles. Or consider this: the Higgs field didn't just give particles mass, it sculpted time. Right after the Big Bang, when the field switched on, it altered how forces like electromagnetism and the weak nuclear force behaved. What if we could rewind that process in a controlled way? Could a Higgs dampener temporarily mute the field's effects, letting particles communicate as they did in the universe's first trillionth of a second? Particle physicists already simulate these conditions in colliders, but what about scaling it up? A region where massless particles zip around unimpeded might revolutionize energy transfer or computing. Of course, the side effects could be apocalyptic. Mess with the Higgs field too much, and you might accidentally trigger a vacuum decay, rewriting physics in an expanding bubble of doom. Then there's the ultimate question: is the Higgs field alone? Some models hint at a hidden family of Higgs-like fields, each tweaking different particles. If true, could one of these shadow fields be the key to dark matter's ghostly grip on galaxies? Or worse, what if we've only found the first domino in a chain of cosmic secrets? The Higgs we know might be the gateway to forces and particles that make our current physics look like cave paintings. So here's where you come in. Which of these cosmic what-ifs grabs you: the warp drive dream, the particle time machine, the dark matter connection, or something wilder we haven't even imagined? Drop your boldest Higgs hypothesis in the comments. Maybe your idea will spark the next great experiment. After all, the universe's biggest breakthroughs often start with someone asking, "Yeah, but what if?" So here we are, standing at the edge of a revelation that rewrote physics. The Higgs field isn't just another piece of the cosmic puzzle, it's the glue holding reality itself together. From the weight of a single atom to the fiery hearts of stars, its invisible hand shapes everything we know. And the wildest part: this isn't some ancient force frozen in time. The Higgs field is alive, humming beneath the surface of existence right now, in this very moment as you watch this video. It's the reason you can feel the ground beneath your feet, the reason light zips effortlessly through space while you stay rooted to Earth. But the real magic lies in what we haven't discovered yet. The Higgs field isn't just an answer, it's an invitation to deeper questions. Why does it have the exact strength it does? Could it connect to dark matter, extra dimensions, or even other universes? Every collision in the Large Hadron Collider, every new calculation, peels back another layer of this mystery. And that's the beauty of science. The more we learn, the more we realize how much wonder is left to uncover. Thank you for diving into the invisible with me today, for geeking out over quantum fields and cosmic molasses. If this journey sparked even a fraction of the awe I feel for this topic, then we've done something special together. Now it's your turn. Keep questioning, keep wondering, and who knows? Maybe one day you'll be the one connecting the dots between the Higgs field and the next great cosmic revelation. Until then, hit that like button if you enjoyed the ride, subscribe to stay curious with us, and let me know in the comments, what's the wildest universe mystery you'd love to see solved next? The universe is full of secrets. Let's go find them.